Hey guys, welcome back. It is 5:40 on April 20th. Today, the big wind just blew over both of my grills, my son's basketball hoop, and my garbage is now strewn throughout my neighborhood. So, yay, it's been fun. So today, what we're going to talk about is enolates with acid derivatives. Now, this will work in some very limited cases. So there's a lot of provisos I have to throw at you here. So the first one is this, enolates. For this purpose, we are only talking base/enolate chemistry. All right? No enols and acids need apply for reasons we'll discuss in just a minute. Also, for this purpose, the acid derivatives that we're going to talk about in question are esters. And pretty much esters alone. So let's take a look at why some of the acid derivatives are more reactive than others. We're going to start over here with the highly reactive derivatives. And over here, let's just show up in this corner a really quick reminder of what enolate chemistry does. So we start with the ketone. We have a base that pulls the proton off, makes a pi bond, opens up the carbon-oxygen pi bond, and you wind up here. This is your enolate. And what I need you to remember going forward here is the old adage in organic chemistry: bases make nucleophiles, with very few exceptions either way. Now, if you'll excuse me, I want to take a drink of my beer here real quick. New Glarus, for those of you who are curious. As blasphemous as it is, I'm not that much of a Leinenkugels fan. So, the highly reactive derivatives. Let's take a look. We're going to include the acid chloride and the acid anhydride. Remember, when you bring your base near here, even though nucleophile chemistry is slower than acid-base chemistry, what you're going to get in both of these is a substitution with the nucleophile and the byproduct coming off the other side. All right, what about the acid? Well, the carboxylic acid, you bring a base near that, what you're going to make is the carboxylate salt. So that really narrows the field down to just a few carbonyl derivatives that we have to work with. Let's take a look. The one that we're going to spend the most time with is the ester. So there's your ester. The pKa of this proton is roughly 25. You can still use hydroxide or alkoxide, more on that in just a minute, to do this reaction. But there are some limitations there. Now, the only other one of these acid derivatives that really has a chance is an amide. Now, the pKa of the amide is about 30. Now, you might be wondering, why is the amide so much higher, 10 to the 5th times less acidic than the ester? And the answer to that comes from, how many of you remember this secret magic form that amides can do, that none of the other acid derivatives really can? Remember this one? I hope you do, because the reason the amide is so much lower in pKa than the rest of that, the rest of the derivatives is, so much higher in pKa, so much less acidic, is this amide, this particular resonance form, I'm going to say, ties up the carbonyl. Whoops. So, less resonance from the enolate. There's less resonance from the enolate capable. So the amide has a lot higher pKa than the ester does. The final one that I want to throw in here, just because I have a soft spot in my heart for cripples, bastards, and broken things, is the nitrile. The nitrile has a pKa of about 25 as well. So the nitrile and the ester aren't that different. You can do a lot more with the ester though. So I'm going to flip back a page real quick and said enolates with acid derivatives. You've got to go through the base enolate pathway, and the one you're most going to use is esters. Now let's take a look at why. Now, throughout my examples, I'm going to be using the ethyl ester. You can use methyl, you can use pretty much anything on the alcohol side of that you want. Esters have a couple things going for them. One of those things is that it is monoprotic. Now, that's a little misleading, so let me tell you what I mean by that. You'll remember on a ketone, you had two sides that you could pull protons off of, and you had to account for those, especially when you had something like an asymmetric ketone. Now, over here on an ester, you only have one side, if you will, that you can pull protons off of. The other one, you can't. Now, another thing about the ester is when you do enolate chemistry through an ester, there's some very specific rules about the base. Your base must be the alkoxide of the alcohol portion of the ester. I like to call this the collars must match the cuffs. A very old saying for fashion. I only know it from watching old spy movies. So, what do I mean by this overall? Well, if this is our ester, we have to use ethoxide. Ethyl ester, ethoxide. A methyl ester, you would use, hold on, got a little ahead of myself here. If it was a methyl ester, you would use methoxide. There's really no reason to go beyond these two. There's no added benefit. The only one I have seen people do, and I think it was just what this research group did, was they used isopropyl esters. And they swore that it helped with solubility. So then what you had was isopropoxide. You had isopropoxide as your base. Now, here's why you cannot use hydroxide. I'm going to underline that a couple times. You cannot use hydroxide. Here's why. So we've got our ethyl ester here. We could use hydroxide as a base and hopefully form this, right? Well, remember, this ester has a pKa of around 25. Or we can use the hydroxide as a nucleophile. And in that case, you wind up here with the acid-mediated ester cleavage. Now, I'm running out of time here, and I haven't even showed you the real reactions yet. So let me get right to the point. Dr. Weigel, you always said that base chemistry is faster than Base chemistry is always faster than nucleophile, electrophile chemistry. How come you're saying that these ester cleavage here will predominate? What's that all about? Well, Shorzy, I'll tell you what that's all about. That is because, yes, acid-base chemistry is faster. But what you get on the other side here is water. And that has a pKa of around 16. So this could potentially work, but there's a huge equilibrium fighting you. All right, I got a minute and a half left. So this is why you can't use base. It's a very similar reason that you cannot use acid. Sorry. So if you have this ester and you decide that you're going to use acid to try to do an enol, this will not happen. The reason for it is the favored reaction would be the acid hydrolysis to the acid and the alcohol. All right, I have 30 seconds here. I can do this. So here's one other thing you have to remember. The reason the collars have to match the cuff with the bases is if you react this with methoxide, you're going to have two esters floating around in your system. Ethoxide and, a methyl ester and an ethyl ester. And that can confuse your product. All right, folks, that's all we got for today. Next video will be about the actual chemistry we do with these. I didn't mean to natter on this much about acids and bases. So stay healthy, stay hydrated, and have some fun.